So this is this is sort of the last paper on the series that we are looking at in terms of operating system reliability and adding functionality. I think it's both reliability and adding functionality. I think all these things are happening because of our desire to add functionality. And one of the things we've been looking at is how do we do that? How do we extend the operating system and still do it in a secure fashion, kinds of stuff, right? And so this paper was actually from SOSP 03. It won the Best Paper Award. And then the paper we actually read was the extended version on a journal paper. So after they get this from the paper, from the conference, they get to go back and add whatever changes they thought was necessary based on the feedback from the conference presentation and what have you. And there's no page limit on journal papers, right? Especially on the talks thing. So they get to write whatever they want. They get to expand it how much they want to tell the story. So if you read the SOSP paper, it would have been a lot more. You can only write 15 pages, whereas here you can write whatever, right? And I'm surprised that you guys are still pretty critical on this paper. I think some of you said it'll kind of it's tolerable kind of stuff. So even though we can find a lot of problems and stuff, I still want you to put things in perspective, right? So the perspective is, if you had written this paper, right, and got into SOSP and got into talks, you can go anywhere you want, right? Particularly if you want to be a faculty, you can go anywhere you want. If you want to go into industry, research lab or something, you can anywhere you want. So it's considered to be like sort of if you get the Best Paper Award, it's sort of like the best you can do in that field on that year, right? So they did a lot of work. I mean, if you see that they did a lot of work, lot of work, right? I think it took him like 18 months for Mike to work on this stuff, and 18 months of full-time work, which is like a lot of work, right? Of course, like every work, so it's only one person, right? So you can't compare with what Microsoft could have done. I mean, again, keep things in perspective, right? The reason why I'm saying keep things in perspective is because mostly for your own research too. You don't want to raise your bar so high that you will never be able to graduate kind of stuff. You want to keep things in perspective, and you want to see what you're able to achieve within that time. So you're not. So one of the things you learn is a lot of the fringe things you mention are nice. Like all your committee, your program committee chair reviews will say things like, oh, it would have been nice if you had done it on 10 more cases. It would have been nice if you had done it on XP and all those things. Those are niceties that people always want, but you want to look at what the core is, what they're trying to do, right? And that's what we are trying to look at here, because that's the important part. Whether they did it on Linux and what have you is relevant, but not so much. I mean, practically they're just students, right? So I kind of wrote down some of the comments that you guys mentioned on the blog thing, and sort of go over some of the stuff, right? So before we do that, so now you can see where all these things fall, right? The spin, you can achieve the same thing that they're talking about here if you're willing to use a type-safe language. If you're willing to use a type-safe language, which has certain performance benefits or what have you. But more importantly, you have to write it in a different language that you may or may not know, right? And the jury is still out on whether that's a good approach. I think people can still keep trying it. I think if you still look at the where the vendors would like you to go, Microsoft would still like you to use maybe Visual Basic or C++ or C hash or there's a Sing hash or whatever language. So they would like to give you a language. They may not tell you exactly that you should go with a completely different language than what you know. Like, if you're used to programming in C, they're not going to tell you that you should use Lisp. But them giving you this IDE and all those things, they can do a lot of stuff internally, right? So if you say you can write C program in any language, any compiler you want, versus you have to use our compiler, right? Our like Apple Xcode or whatever. So they can do some of the stuff. So maybe it won't go all the way what Spin wanted to go, but sort of in that direction. Kind of force you not do whatever you want, but kind of force you. The other notion is a little bit more complicated because it requires the logic stuff that that we are kind of skeptical on how well it can scale. But for the cases where that can work, this is very elegant because you can write it in whatever you want, and the performance you get almost. For the running code, there's nothing that stops you. There's only a gatekeeper, and the challenge is how do we build a general enough gatekeeper the proof carrying code where the security proofs are faster to generate, easier to generate, fully automated, and the predicates are easy to generate and all those things. But if you can do those, this is the best in terms of performance, because once you're in, because it's basically doesn't have to do any checking. So the Nooks approach is, they would argue, a little bit more pragmatic. They are trying to leave the same host drivers. They put wrappers around it to make some modifications, and they play a little bit games with the protection, right, on the hardware. We'll see what those are, to protect against some faults, right? And they do a good job of explaining what they want to attack, right? And they do not want to attack malicious drivers, right? Malicious drivers they don't want to attack. There are two reasons. One is it's very hard, right? Because once you go into malicious code, then you're going into a different area of research, right? So if I assume that your bugs are caused by your making mistakes, then I can do some things. But if I assume that you're an adversary and you're trying to do something to hurt me, then we get into this arms race. Then it goes to a security area where things become different. So the elegance of what they're trying to do will completely vanish, right? But their assumption is most drivers are not malicious, right? How many of you believe that? If you don't believe that, you cannot use your drivers, right? I mean, like the example, you have 18,000 drivers or whatever, right? If you don't believe the drivers are not malicious, you are in for a surprise, right? Most machines have enough drivers, enough modules that you're loading in. And it's not possible for you to look at the code and see what they're actually doing for every driver that you have. Right? Even if it's on Linux, it's impossible for you to look at all the code, and especially if you're on Windows or something, you have to trust these things. So if you don't trust the drivers right now, you're in trouble anyway. So Nooks is not going to make it any more worse than what it is. So if you trust your drivers, you have to load the drivers. If you don't want to load the drivers, then your current machine is useless to you. But if your machine is useful, they can do something about it, right? And that pragmatism actually helps them go far, because if they want to protect against malicious code, that's a good problem, but that's a different problem that people are solving in a different fashion, right? So how do they do this stuff? What's the key ways that they achieve this sort of pragmatic solution? Yeah.
They sort of isolate the driver code from the kernel code, and just to make sure that the driver can't really corrupt any of the kernel structures.
So how do they do the isolation here?
They give the driver their own address space, and that way, well, I mean, in the sense that for a non-malicious driver, it has some address space. And then in certain data structures, they'll copy from the kernel into the driver address space if needed.
So do you understand how the own driver's address space works, right? You understand exactly what they are doing here, right? So they want to isolate. They want to create a container for their own driver, right? So one way to do that is sort of like a Java, right? You can put them inside their own firewall sandbox container, and then you can run with it. And then it becomes, all the performance issues and all those things. You don't want to do the full container. The other approach is to put them in a different protection domain, right? So instead of having user and the kernel, you can think of it like a driver domain, right? Where it has certain privileges and stuff, which normal machines don't give you. So normal machines only give you supervisor and the user privileges. So their challenge is to come up with a protection mechanism which will protect your driver. So your goal is, if you have your kernel and you have a little driver, right? The challenge is, if there's a bug here, right? If you have certain kind of bugs, if you have to do a code dump or whatever, right? Or access a memory location that you're not supposed to access. If you have a fault here, the whole thing comes down, right? The whole machine has to come down, because there's nothing you can do, because you don't know how to respond to that, because it's happening inside a driver, right? The way you want to protect is to put them in a sandbox, right? Where this one does not have privileges to do all the stuff that the kernel can do, right? Remember, applications cannot do certain things, but kernel can do anything that the machine can do. So when you're inside the kernel as a driver, you can do whatever you want, right? So they want to isolate this stuff, except hardware does not give you this notion of this protection boundary, right? So the way they address that is to leave this in the kernel domain, right? So it will have all the privileges of a kernel, right? So this is user. User cannot do certain things. They cannot change the page table or what have you. Over here, you are still inside the kernels. From the hardware perspective, you can do whatever you want. You create a new page table. You control when you can go in and out, right? When you go in, you change the page table such that, let's say the page table says, let's say there's a page here, right? You can change the page table such that if you're running in this area, you make this read write. If you're running in this area, you make it read only, right? By using the page table, right? So you have to control when you can go in and out. So you have to have this notion of a XPC or whatever, some wrapper, which basically says that anytime you're trying to go into this driver, anytime you're trying to access out of it, you control it by changing the page table, right? So from a hardware perspective, you can do whatever. That's one of the things that they mentioned, right? If you wanted to change the page table back to whatever you want, you're free to do that. But normally well-behaved driver programs would not know about those stuff. So any control which passes in and out through this stuff, you change this page table such that a page which you would have been able to write before, now you can only read, right? So if you try to modify this page, you'll get a page fault, just like you would do for any other case. So when you get a page fault, this wrapper can say, okay, you're trying to modify something. I'm going to make a copy of it in here. I'm going to let you modify it here. So you won't corrupt the whole operating system. You modify it here. And when I think you're done, I'm going to copy it back, right? So I'm going to cache this stuff, right? So I'm going to play games with the memory, the paging system to change certain pages to change the protections from you so you get a page fault, right? And the reason why they don't have access to malicious code is all this depends on the manipulating the page table, right? And since you are a super user, it's very easy for you to change the page table if you really wanted to, right? You can't protect that. The only way to protect that is to put you on a lower protection domain, which needs hardware support, which machines don't have, right? So you don't. This is the best you can do, right? You're changing the page table and you're achieving all this, all the stuff, right? Have you seen this kind of a behavior of using page tables to manipulate to do different stuff? Of course, we're looking at the memory stuff next, right? But you must have heard about this concept of using page tables and changing the bits on it, read, write, and what have you bits to do certain things, right? Does anything pop out of your when you think about that? Have you heard of cow? Copy and write? How many of you heard of copy and write? So you guys haven't heard of copy and write. So what is so this only three heard of copy and write. So what's a copy and write?
When you fork the process, as opposed to copying the entire address space immediately, you wait until the new process or the old process changes something, so that the two are different before you copy the entire page that was written.
Yes, optimization used for fork, right? Fork semantics expects you to copy the whole thing. You avoid that by changing the page table such that both of them have the page made into read-only mode, even though semantically they should be read-write. So when you actually write something, I get a page fault and I do something, right? And it's sort of a similar idea here. I mean, you're going to do this stuff. And the thing that they complain about in this whole model is they're stuck with whatever the x86 or the PC that you buy, right? What happens is when you do the page table switch, it flushes the TLB, right? Which means that every time you go back and forth, if you change the page table, you also pay the cost of TLB flush, right? And more expensive hardware, they don't force you that. I mean, if you had hardware support, if you use a TLB with the tagging, then you can tag that this TLB entry belongs to kernel and this TLB belongs to this driver. So you don't have to flush it all at once. You can flush it when things are needed or what have you. So I think the main performance loss comes from that particular fact, that the TLBs on the regular x86 will be flushed every time you do the space switch, right? And it's very easy to fix, and it needs a modest amount of hardware. It's in most workstation level machines, right? So I don't really hold it against them because it's one of those things where the hardware manufacturers have no reason to put it inside a PC because the current generation of Windows XP cannot use that, right? But I don't think the cost to put it is high enough that it's one of those things that they would have put it there if somebody wanted it. So if you say I want it, the cost would be like maybe a few bucks or so, right? So once you do that, the overhead is not that much, right? You have to capture every time you do this stuff. So the main performance penalty that you face is that every call which goes through this XPC is a problem, right? Otherwise, you get to do the same things, right? Except if you have to do this copy once in a while, and for the most part, it's acceptable because it's amortized over a period of time. XPC is the one which kills you, right? So that's the stuff. They achieve protection by using something on the page table, right? And whatever you can do, whatever you can capture like that, you are fine. So if you had a while loop inside here, if you go into while one loop here, this mechanism won't catch it because you're not crossing the protection boundary, right? I can monitor whatever you're doing when you're calling the kernel and back and forth, but what you do inside the driver, I don't know. So if you're inside the driver, if you go into a loop and you're doing nothing, then there is nothing I can do. If you get into a deadlock inside the driver, then I don't know what to do because you never call the kernel. I mean, there's a bug inside your driver, exclusively inside the driver. So in that case, there's nothing I can do because I can't peek into your driver to see what you're doing. All I'm saying is, I assume that any bugs caused by the driver mucking with the kernel data structures, I have to capture. But any bug that is caused by you doing something internally, it's okay, right? So they do capture some of the bugs that they mentioned that is not done. So if you free some buffer, right? If you free this buffer, then I know that because I know that you're removing their association with it, right? If you use it later on, then I know it because I manually removed the copy that I made for you. So if you try to modify it, I capture it. So there's some bugs that they can capture, but for the most part, that's not their focus. I mean, they're not trying to find bugs. They're only trying to find that the something, right? And the other assumption that they make is it's not code that fails every time, right? If a code in a guaranteed fashion fails every single time you use it in a certain fashion, the assumption is it's probably bug fixed, right? It's dealing with hard to fix bugs, dealing with bugs that are quite rare, and they assume that if even a bug happens, you can recover from it basically by resetting the driver, right? So it's not designed for bugs which happen all the time. So if you have a bug where every time you load the card, there's the driver crashes, right? If you do this, it'll crash. You reload the driver, it crash. You reload the driver, crash, infinite loop. So you're still out of luck, right? So if you have rare bugs that can be fixed by rebooting, and the logic is most of the times when you reboot the machine, things work fine. So if you reboot the machine, it works fine. That means that particular driver, that bug can be kind of masked by resetting that particular driver, right? And there are other class of bugs that these approaches cannot solve, which is a problem with the driver or the hardware itself, right? So when you reset the stuff, sometimes the network card may go dead. The network card is no longer trying to do something. So if you have a cheap enough card or a buggy card, sometimes when the driver goes off, you probably have to power off the machine to bring it back up to reset it, right? And they mentioned that some of the times it happens, right? So in those cases, you resetting the driver won't help you because you reset the driver, but that does not actually power cycle the actual card, right? And there's no way for you to know that because from software, you reset the driver, but you have no idea what happened, right? You're smiling. So you face those?
There's a new, in the alpha version of the new Linux kernel, for a specific network card, the driver actually bricks your network card.
Okay.
So if you run into that problem, resetting the driver really isn't going to do anything because your network card is now bricked and doesn't work at all.
Brick meaning like
yeah. It does a firmware flash somehow, and the network card doesn't check to do any kind of sanity checks on what you're trying to flash to it. So it's like, okay, I'll flash to it. Oh, now I can't do anything because everything's broken.
Okay, so those kind of bugs are rare, right? I mean, those kind of bugs where the card is never going to be used again is rare. But a lot of times when the card goes into a weird state, I've seen it a lot in video cards, right? Whenever video cards have to reboot, they don't reboot nicely. I mean, you probably have to power off, power cycle, and do the stuff, right? So video cards typically they don't crash as often, but if they crash, you may have to power off and wait for the whole thing to drain out before you start the stuff, right? Network cards get into the stages where they're in a weird state where they no longer get IP addresses, they're in weird state. Some of you may have seen those errors, right? Some of the times a network card may not work properly, right? And the hard disk drivers usually are better at resetting because the hard disk itself needs resetting once in a while. So you may notice that if you're doing a benchmark of something, you may notice that suddenly the hard disk would reset itself and then come back, right? So typically hard disks are better able to recover from resets because they reset by themselves, even normal behavior. So in graphics cards, if they reset, nothing happens, right? One of the ways you would have seen this is how many of you use a laptop in a power save mode, like where you make it sleep and then make it wake. How many of you use the laptops or something like that? So what do you guys? What do the other people do? Like, do you use like desktops or?
We're using Hibernate.
Okay, so one of those things. Yes, sleep or hibernate or whatever state, right? But I'm saying you're trying to put the PC into some mode and then you're trying to revive it, right? So how many of you do that in either laptops or desktop? Or how many of you don't do any of those? Okay. So 4 of you don't do, right? So for the rest of you, right? So you didn't. So what do you do? Hibernate on the desktop.
Laptop.
Okay. So do you know what happens when you hibernate or when you put the card to sleep? Yeah.
Does it have to copy all the system state to the hard drive or something?
Yeah. So hibernate typically you mean that you put it into hard drive, right? And sleep you usually put it into memory, right? But regardless of whatever, you put the state, you want to put all your current state into some other device. And then when you come back up, you want to restore all the state from that device and then proceed, right? So if you put it into hard disk, essentially you're trying to freeze the whole machine by putting all the state into the hard disk. When you come back, you have to have some firmware support, which essentially takes everything from your hard disk back into your machine and make it go, right? So if things work, you should be able to hibernate, and when the hibernation starts, the whole world kind of stops. And when you come back up, it'll get you back to where it was. So the time will go back to just before the thing starts to go, right? How many of you have ever had any problems with doing that? So what kind of problems do you face?
Well, so like I have a laptop and I put it in sleep, and I can wake it up, in an hour. But anything longer than an hour, I cannot wake it up.
Okay. What do you mean? Like you cannot wake it up? You'll have to reboot, right?
Yeah, I have to hold the power button for half a minute, to power it down and then restart.
So you use sleep or hibernate?
Sleep.
Yeah. So it looks like your memory was gone,
Yeah.
right? The state was gone, right? So what are the problems people are seeing?
It's never as fast after it wakes up as when you shut it down. Like if you shut it down and you wake it up again, it's like it just seems to be slower than before until you restart.
I can't explain that one, right? Because if it works properly, so hibernation has to be done by somebody else other than the operating system, right? Operating system cannot put itself to sleep because if it has to do it by itself, it'll have to save all the state, right? But the thread which is saving the state has to be put to sleep, so it can't kind of do the stuff, right? So you usually use a firmware to do that, right? So when you do the firmware, operating system does not really know what's going on. So it's basically going to say, save all my state, restore all my state, let me go, right? So there is no reason why you should be slower after that because the new machine, all the tables and all those things that the software had should be the same. So I have no idea why it's slow, right? But you see those kind of bugs, right? And you cannot say, oh, that shouldn't happen, right? But obviously it's happening, and dealing with those kind of bugs are very hard, right? So that's one of the things that they don't want to get into because debugging that problem, it makes no logical sense why it will be slower, but obviously it's happening. So how to deal with that? Nooks will say, we don't know, right? Is there any other way that things fail for in hibernation for some others? Yeah.
Yeah, I know some experience about that. The USB driver, some Linux, a few versions back, I come up and compile a kernel myself. The Linux USB driver is unloaded, and when we wake up, it's off. It's gone.
Yeah, so that happens a lot, right? Like one of the things I've seen is the graphics driver goes something bizarre, right? When you restore it back, the screen is like white or something, like just white light, not displaying anything. And you can remote log into the machine. The machine is fine, but your graphics thing is short, you can't do anything. And you have things like these fail, your USB driver and all fails, right? So what happens is when your machine boots up, your firmware has to restore the state of all the stuff. So it has to restore your USB driver or whatever, right? So the way it restores it is first it'll reset it to make sure that the driver is in some sane state, and then it'll load whatever state you had, right? So whatever state it was, it'll try to load it. And depending on the driver, it may or may not be easy, right? So if it's a hard disk kind of things, you reset it and then you issue new commands, right? Whereas if it's a graphics card, you have to restore the graphics memory to where it was and all the state of all the stuff to where they were. If there are any bugs in those, when you do this reset, it doesn't quite get back, right? It doesn't quite do the stuff. So you notice these kind of bugs where suddenly you can sleep and awake 10 times in a row. On the 11th time, your USB card kind of dies, right? And your machine is fine, it seems to work fine, but your driver is not able to restart. And that's one of the things that they were saying. If you have issues where your driver cannot restart something, then there's nothing Nooks can do. I mean, that's a hardware bug or some bug that they can't deal with, right? So for the other cases where it's easy for you to reset the stuff, so for a vast majority of the cases, turns out this is not a bad approach. I mean, this is a nice approach to do this stuff. And the main performance that they problem is this TLB stuff. But that's we know how to do that. I mean, it's just that they just had machines which didn't have those stuff, right? So going back to the comments that people had, right? And I think one of the comments was a lot of the driver bugs are because of version mismatches, right? How many version mismatch of the kernel and the particular driver? How many of you believe that? Or yeah.
I believe it.
So how do you get version mismatches between the driver and the kernel? Obviously, between Windows 95 and XP, there's going to be a different version, right? So if you take a Windows 95 driver and use it in Windows XP, all bets are off, right? I mean, it has to be all bets are off because that's a different operating system, right? Is there another way where there could be a version mismatch, which is a lot more harder to deal with? Right? Yeah.
So when you upgrade a kernel version, you have a driver and then you upgrade the kernel version,
Mm-hmm.
you have the drivers are all compatible.
Yeah, so the normal way that you do that is through applying patches, right? If you're in Windows world, normal users don't think of upgrading the kernel, they apply security patches, right? So you get something from Microsoft or Linux or whatever, right? So for people in the know, you know exactly, like, so you'll ask, like, so what version of kernel are you running? And they may say for Linux, you're running 2.4.18.1.1 PL2, blah, blah, blah kind of stuff, right? But in reality, for the Windows world, it's whatever Microsoft sends you. So if Microsoft sends you a new patch, right, then you have to upgrade all the drivers to work on the patch. Even though the patch may be small, there may be version mismatches because the patch that you downloaded, Windows SP1 or the security patches which seem to come every so often, right? They're changing the kernel, right? So your driver may have worked fine before, but no longer works. And it's one of those things where you're constantly going through this patching process without. So it doesn't have to be as bad as running a Windows 95 driver on Windows XP. It could be as good as Windows XP driver working fine, Microsoft patches their kernel, that messes up something, it fails, right? The other approach, other thing that RDC mentioned is the sheer combinations of all these things is staggering, right? So, which I think is one of the reasons why people like Mac, because Mac kind of cuts down all the stuff. So if you have 18,000 different drivers, right, it's possible that your machine and her machine are nothing alike, right? They're completely different in terms of the hardware. So even though they may be running Windows XP, the drivers that they're loading is completely different, right? So we need to know how all the drivers you have interact with each other and the kernel. So it may fail for you, but not fail for her. So to be able to check this, you need to have infinite number of combinations of machines where you say, what if I have this network card, this network card, this network card, and then this graphics card, and find all the combinations, which is not possible, right? So that's one of the reasons why you get version mismatches and driver mismatches, because you have different kind of card. And in the PC world, it's even worse because you may have bought the same. So frequently one of the things that if you're working on operating system kind of stuff, the thing is you ask let's say you buy from a vendor and you ask them for 10 PCs and you tell them I want this particular card, blah, 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 like you give all the specifications, and you find that between the same versions they switch something a little bit, right? Which may or may not matter to you, right? So it's possible that you had USB driver version 3.0.1 or something, and somebody got a 3.0.2. The firmware a little bit changed. So within the 10 machines, one of them may be different than the other, and those things fail. So the problem is really hard because of all these changes, right? It's very hard to kind of keep into one version. And yeah, the TLB overhead, some of you mentioned, and that's the price you pay, right? And I still feel that that's an unfair cost to put against them, because we know how to solve that. We know how to have the TLB tax. It's been around since mid-90s and stuff, so there's no reason why the PCs won't have those, right? If the PC vendors are willing to put TPM and other more complicated stuff on the stuff, this is the simplest thing to do. Make a TLB with a tag, right? And if you can solve all these problems and let you have some performance bounce, then it's a good thing, right? And then the other comment that I think Ryan had, which is the number of crashes versus the overhead, right? And that's the big stuff. I mean, one of the things that they mentioned was Windows. I think 5% of the Windows machine crashes every day, right? So the notion of how much is a crash worth to you, right, and how often it happens, right? So the way I read it, your point is you don't get crashes that often, so this is not that worth to you, right? So what is the sense of others? Do you face crashes often, or if you don't face often?
Well, it's not only just a facing crashes often, but it's a function of how often you face crashes versus how much it costs when you face a crash. And my cost when I face a crash is a couple expletives and a reboot, not losing 5 years worth of data and $1 billion in lost sales. Which, if that would be the case, then I would be much more likely to run this.
Yeah, it may not be lost sales, but maybe lost thesis, right? Which is 5 years lost thesis is a lot more worth to you than whatever. Yeah, I get the point, right? So, what's the other sense on? What is your experience on kernel bugs? Have you faced them?
No, not really.
Ever?
No, well, my XP64 bit, I've not had a crash in over a year. So
Okay.
it's been excellent.
Have you ever had a crash or none?
No,
Do you use it often?
yeah, every day.
But you never had a crash.
No.
Do you reboot every day or?
Usually a couple times, yeah.
Okay. That's one way a lot of the companies deal with the stuff, right? With Windows XP, they reboot it every day or so it kind of cleans those things up, right? That's one way to go, right? And if you control what goes on the machine, and if you reboot the machine, then you're protecting your machine from doing that. What about the others?
I don't face crashes very often.
So you do face crashes at some point, right?
Yeah.
You've seen crashes, right?
In the past, I used some old versions of Windows. I faced crashes very often. But now, things are much better.
So how often do you think you face a crash? Once a month, once a year?
You mean
No.
the older version?
A newer version?
Oh, very often.
No, the newer version I'm saying.
A newer version. Now I use Vista. I don't face
No crashes at all? So
much better.
So I mean, I'm saying, do you face crashes at all, or like you don't face crashes at? You face it like once a month or so. Once a month, let's say.
You mean Vista? Or-
Yeah, with the Vista.
Yeah, about.
Once a month.
Yeah.
So how about the others? You guys face crashes? So are you guys like different that none of you face crashes?
Well, I can crash Windows XP anytime I want.
No. I'm saying like normal usage, right? So no, I'm not talking about stuff that.
So yeah, I have like a webcam,
Okay.
and it had to go to a specific USB port.
Yes.
If I put into another USB port, it crashed.
Okay.
So I mean,
So what I'm trying to get to is like his stuff, right? He mentioned that the crashes are rare, that it's not really a problem, right? So I'm trying to find, see what happens when you have lots of crashes and crashes very rarely, right? So my hypothesis is if it crashes often, you behave certain way because you know the system would do certain things, right? If it crashes very rarely, you behave certain way, right? So I'm trying to see what's the cost of your behavior on what you're trying to do, right? And does that make sense?
I think it's like if your computer crashing every day, then probably just go out and buy a new one.
No, I mean, so let's assume that you have no such choice, right? I mean, so that assumes that you have a choice between a crashing one and a non-crashing one, and you choose the crashing one to begin with, right?
Yeah.
Let's ignore that part of it, right? So you assume that there's a reason why let's assume that you made the good choice and you bought something which has crashes, right? Because otherwise it seems kind of weird, right? Why would you buy? I guess that's why people buy different operating systems and stuff, but right? So my point is, if it crashes often, I think you do certain things differently where you try to avoid the stuff. One of the things that, at least for me personally, when I work on a machine which rarely crashes, I tend to leave a whole bunch of state in the system. I tend to leave lots of windows open with lots of Emacs sessions going on for months and months. So when I get a crash on that machine, I'm a lot more in a really bad position because I tend to trust this machine, so I have a whole bunch of states. So now to get back to the thing, it's so much harder because I had like 15 files open on different stuff, which has not been saved kind of stuff. But if I'm working on a machine which crashes often, right, you tend to do stuff a lot differently, right? You tend to save often, but not rampantly. You kind of tend to make sure the machine is like working fine before I save the file, right? And then you kind of proceed and stuff, right? So my point is the cost of crash sort of equates to if the crashes are rare, then the cost of that one crash is a lot more because I have a lot more stuff that I'm doing which I shouldn't have been doing. Whereas if it crashes more, then I do certain things differently, right? So the bottom line is crashes are always wrong, right? You see anecdotes of those, right? You see Murphy's law always kicking into this stuff, right? You see, like you go to the conference, it's highly likely that Michael Swift's laptop crashed before he was giving a talk at SOSP, right? You see those stuff, right? You see something like that fail, or you see like you connect the VGA adapter for the conference projector into your laptop and it crashes, right? You may have seen that. If you haven't seen that, you will see that, right? You see like in the worst possible cases. So when you're sitting in the like at the end of the semester and you say, I have nothing else to do, I have 3 months I'm going to sit at home, and now the machine can crash all at once. Your machine, I can guarantee you, will work perfectly fine. But those times, right? The other times that you're actually doing it. So, but the important stuff that they kind of mentioned, which I don't think they can cite the reasons behind what happened, was the philosophy behind when to crash and when to let go, right? So they said Linux is a lot more forgiving in terms of bugs, right? So they have two notions of process and the interrupt kind of bugs, right? So if you have a device driver, then it's interrupt-driven model, right? When something asks for some service, you do something. Otherwise, you're not doing anything, right? So in that model, Windows tries to apparently crash often to save you from corrupting some data, whereas Linux forgives you where there is a bug which is corrupting something and lets you proceed because you like that. Did you see that argument? I think they made it like at two different places, right? So the philosophy of Windows was they crash often to protect you from corrupting something later on, whereas Linux actually forgives and goes on. So some other cases where it should have crashed, it does not crash because it forgives you for what you did, right? What do you think of that? Does that let's assume that Windows actually makes a conscious decision that some of the bugs, even at the slightest hint that there's a bug, they crash, whereas the slightest hint of bug, Linux lets you move forward, right?
Overall, that should theoretically increase the quality of the drivers, because if a bunch of people notice that their systems are crashing all the time, they're going to send some of them, a small subset of them, we're going to send bug reports to Microsoft, and Microsoft will get the stack trace, and they will go yell at the device driver manufacturers that their stuff's crashing. Or Microsoft fixes things, which I thought was actually very interesting in reading some things, is that Microsoft actually goes in and fixes their code to work with other people's device drivers when they do things that they're not supposed to do.
Did they mention that in the paper? I forget.
No, not in the paper, but there are some blogs about a guy who complains about all these different software manufacturers saying, you know, they went three levels up in the stack trace to get some random local variable which they could have gotten through using this normal API call. So since the compiler changed, to change the order in which things were stored, so now the byte offset was different. So now they crashed the whole system, but we had to go back, and so yeah. But that's a totally different tangent. But the fact is, I think the crashes will eventually. At the beginning of XP, I had a lot of problems with crashing, but now I don't have any problems. So I think it's a lot of the drivers got better.
The XP has been around for a long time too, right? So
right, and I think and naturally drivers are going to get better as time goes on. So I think that with crashing, there's an obvious problem, whereas with okay, let's just continue. There's going to be latent problems that might not be easily found if they don't usually or often cause problems.
But that's one way, right? Like, you know, the bugs may not be found, but the other problem is it may corrupt something which may affect you later on, right? I never thought of it that way, that crashing is actually good for you, right?
I guess the problem with just crashing and interrupt problems in Windows is that you don't know exactly what they're doing, and sometimes the file system can get corrupted very easily from issues from just abrupt crashes. So they may not actually be saving any data if they, corrupt your.
Yeah, so if it crashes, it crashes, but it won't do any more harm than, it won't do any more harm, right? Than other than the inconsistent state being left, right? I mean, the main thing you notice is like files are kind of left dangling, right? And that's the only thing you deal with, right? But that's interesting philosophical difference that, whether you should crash now or let it go. In the short term, it looks like it's a good thing. Sometimes if I can get like one more minute, I can save the file and then move forward. But the realization here is, when a bug happens inside the kernel, right, it means that this driver did something that it's not supposed to do, right? So it could have done anything. It could have read some data which is not supposed to do. It could write something data it's not supposed to do. It could have written into the buffer that is being used for writing files, right? So even though you thought that the file was still there, even though you want to write the file, this driver caused some difference, change some buffer which happens to be for a file. So if you let it go, it'll complete, and your file would now have the data that was overwritten by this one, right? And that may be a bad thing, right? And it sounds like this is such a bizarre case, right? But even the Mac, till I think 10.3 version of the kernel, they had a bug where two files can point to the same block. It happened often, right? It happened often enough that you have to run the disk warrior every so often to find the problem, right? So what happens is you have one file and then you have another file. This particular block of this file points to the same physical block, right? They have a problem with the clustering. So to find it takes, for my laptop, it took like 16 or 17 hours to run it through, because it has to look at each block. It has to try to look at each file. It has to see where each file is pointing from each block. And it's a very slow process, and it now is like faster, right? So that bug was there for a while, and you don't notice it. You don't know when it happened, right? Because what happens is, if you look at this file, the ls would be the same. Then nothing changed, right? Because the size of this one is the same, this is the same. All the writes on this will go through. All the writes on this will go through. The difference you find is you have a text file, and suddenly you have some gibberish from some other file, which you don't know where the file is because you just see the blocks from that one, right? And those are the hardest thing to debug because you have no idea where things happen. So you have to keep these things consistent, right? So in that case, I would have preferred the cache to have happened rather than do this stuff, right? I think they fixed it now because I don't see it happening much now. But there are oddities like this, and so that's a good way to look at the bug what happens kind of stuff, right? And one of the arguments that some people had was the amount of code that goes in for making Nooks happen, right? So what do you think of that comment? That the amount of code, it's small, but the amount of work they have to do was fairly large. I mean, it looks like they had to look at each driver and they have to do something, right? Is that a problem that we should, I mean, obviously we should worry about, but what do you think of that? Yeah.
It doesn't really seem that important. I mean, if Microsoft were to use it, they could write that into the kernel and presumably the change in the kernel could be ported forward. So.
Yeah, that's one way to look at it, right? So they had to look at all the drivers to understand what's going on and stuff. But this is really meant for Microsoft, right? So if one guy can do this and get a paper out, Microsoft should do this. I mean, you would like this to be part of the system, right? Where Microsoft, before they do all the stuff, will go through the stuff. I'm sure he didn't do as good a job, right? I mean, I don't think he understands Linux as much as Microsoft should do its own operating system because they have hordes of programmers. So it'll probably take them longer, but they can actually do a better job because like I'm guessing that within the Microsoft, you will be in charge of writing network, manipulating network drivers. You guys aren't this, you guys aren't something. So so it is kind of bad. I just ignore those because if you do implement this stuff, this will be done by professionals at each level, so they can do these wrappers, right? The clean idea is your driver, as long as it doesn't have to do some things, you should be sort of okay, right? It's still better than the optimization you mentioned, where Microsoft goes and fixes,
Right.
backward compat, restores a bug to keep a driver going, right? Yeah, and it doesn't deal with malicious code because that's a whole can of worms. You don't want to open it because it's an awful thing, right? So one of the comments I think I found from your thing was, does it work at all, right? The challenge is you're concerned whether this whole process works. So what do you mean by that? Yeah, you.
That's awful. I don't like that design decision that they made to type password in plain text in the password box.
Right, plain text?
It said password in the password box when you logged in. And that's really scary because I wouldn't know if I should type my password because I wouldn't know if it was going to come out clear.
Oh. Yeah, trust Microsoft. Can you see? What really bothers me is I cannot save my preferences, so you have to do this every time, right? For some reason I can't save, like, don't lock it while I'm in the class. So you said, but is it really, overall the authors state that Nooks provides a good reliability improvement, but is it really so is another question, right? What do you mean by that?
So they're saying that the Nooks isolation and recovery services is worth the cost that the penalty that we are paying in the performance. So the question is it really that worth?
So what do you think?
I don't know. 60% decrease in performance is.
So the key is it's not for all the cases, right? It's only the cases like we mentioned here, right? In the case of too many XPC crossings, and there's a simple solution to fix that. So we look at the slides they had for the SOSP conference. It's one of those things which really frustrate you as a OS developer, which is you have to jump through hoops because the hardware does not do what you want, right? But then you realize that if the hardware, what they have to do is fairly simple, trivial sort of thing, the hardware developers would put it if you wanted it, right? It's a chicken and egg problem, right? Intel has every motivation to add stuff if it can get you all the benefits you wanted. So it's not too much of a problem, right? So in this case, tagged TLBs have been around forever, so there's no reason why they couldn't put that, right? So in that sense, the performance would be bad, right? But also the cases we're talking about is sort of pushing the envelope, right? So they're looking at the gigabit Ethernet kind of stuff, and for normal stuff, it seemed to be okay, right? So it's a balance, and yeah, all of these things you have to worry about whether it's worth it, but it seemed like a decent choice, right? So I'm going to look at the slides from them. I kind of rearranged the slides so it's a little bit more lecture oriented, right?
So why did they try to get a system where the TLB had the tagging?
What?
Why didn't they try to get a system which had TLB tagging so that they could install Linux? I assume Linux would work on it.
Yes. So that's another problem with the experimental setup, right? Because then people would ding you for, they could have done that, right? They could have taken a server machine and then put this on the stuff. You could argue that they were being honest and really bought a commodity machine, right? I don't know. I mean, that's the judgment call that comes to when you're setting up the experiment, right? Do you kind of tweak the hardware to do what you want to make you look good, or just get a normal machine?
TLB tagging, that's basically what you want to benchmark it against, because you're saying that basically their hypothesis is it's easy to add to x86, but it hasn't been added yet. So we're going to test it on this benchmark using TLB tagging to show you what performance you could actually expect.
So here's my hypothesis, which I have no reason to believe is true, is they didn't know this till the very end. They did, so they do the page table swapping, right? But they didn't realize that the page table swapping also flushed the TLBs till somebody else told them, because, I mean, how many of us know what really happens in Intel architecture, right? So he went through the project. So remember, this is a journal version. So it went through the conference, and somebody from Intel might have said, "Oh, I know why you're 60% off because of your TLB, right?" So they did actually do experiment to show without TLB tagging what will happen, right? They tweaked it somehow, right?
I
forget what they did, but
I think they just ran it without any protection.
Yeah, and then they show that if you had TLB tagging, this will be very fast, right? So that looks like they kind of added in. So they didn't know, and they were honest enough to say what happened, but it's just not possible for them to go back and fix this stuff, because you get a paper out, then you kind of want next one, right? I mean, you know how easy to fix, but that's a good point. So that's my theory, but because nobody wants to make their own paper look worse, so I'm sure that's not their point. These machines are not that much more expensive that they couldn't have afforded those, but so you may realize some of these you may see some of these authors before, right? So do you recognize any of these authors from prior paper? Yeah. So in which paper?
More than one.
Yeah, but one of the papers that he was involved with Mark, right? He was at CMU, did the Mark thing. He was part of the Spin. Spin came out of this group, right? This bunch of people, right? So Spin came in 95. So it's sort of them going back and saying, okay, we said this in 95. We could solve this in a beautiful fashion without all the stuff by using Modula, but doesn't look like Modula is going too far. But so we're improving on our own kind of stuff, right? So if 5% of Windows machines crashes every day or so, and we have to believe that that's a big number, right? I mean, I find it annoying because I actually think my machine doesn't crash all that much. It only crashes when I close the machine because I have a driver bug in the sleep thing, and it hits randomly. So now I know before I close the lid I have to save something. Except sometimes I forget and I close it, and then it crashes, and you're not too happy about it. And one of the main causes of most of the bugs are drivers, which is not hard to imagine because there's a whole bunch of them, right? They cause 85% of the bugs, and they're a lot buggier than the Linux kernel. for the simple reason that bugs are a bigger part of the code. So even if they were debugged as much as the XP kernel, there's a lot. If there's 80 times more code, it's possible that it has 80 times that many bugs. The other problem is Windows XP, the base, is probably debugged a lot more because all of you run the base, whereas only you may run a particular driver, somebody else may run a particular driver, and so on and so forth. And like I mentioned, so if you're in the business of doing drivers, right, you have to know exactly what version of card you have. So you may find out that 3.0.1.7.v.1.2 firmware has a bug, which was fixed in v.1.3, right? So as a driver writer, you have to look at all the combinations of the hardware that you're dealing with and how you interact with other drivers in the machine, right? And it's not possible for any one human being to make sure that all the machines are works across all the stuff, right? So you would argue that Dell, when they sell the machine to you, would make sure that all the drivers work against all the other drivers when they send to you. And then Microsoft patches it to make it to a different kernel, then all bets are off. So you have this constant race going through. So they built this Nooks, which provides 90% of the faults in their own tests, right? And this is another area that they rely on other people's work, which is how do you inject faults and how do you make sure these faults are accurate, right? I think they did a reasonable job of showing that these are reasonable bugs. These are randomly created bugs. And of course, you need more testing to see how it works in real time, in real bugs, and whether they detect that, right? That's ongoing work, right? For example, what will happen if you take a normal Linux machine with a normal driver which has a bug, not a random one? How many of them will this catch, right? And that is way beyond the scope of what they can do, because so I think they did a phenomenally lot of experiments to show that. Like 400 different experiments, which means that imagine 400 experiments on 400 kernel crashings, right, or reboot cycles, right? So you have like one graduate student probably sitting in front of the screen, seeing 400 times reboot, measuring some things, what happened and all those things. So this is, so if you did this and you wrote this paper, you deserve to get whatever you want because you did the blood and sweat, right? So here's the illustration of what happens. When you have a driver, you load it to the kernel, it belongs into the kernel because it is inside the kernel protection. So if you have a bug, right, and bugs can be any number of things, but essentially if you have something which wants to crash the whole thing, the whole kernel will crash, mostly because you have no idea what it did, right? It could have been a simple thing where it corrupted something inside where you can reboot it, or it could have been that you wrote something here, right? And you wrote something that you're not supposed to, and the kernel has no way of knowing what you did. It knows that you did something you're not supposed to do, and the whole thing will crash, right? So this could be caused when the driver has a bug where it crashes every time. Every time you put the card, it crashes. That's a boring problem, right? Here, you have a good driver which works most of the time, and some corner cases it fails, and that's what you want to deal with. So the vision is if you have a driver problem, you somehow recover from it, right? Recover here may or may not mean what you want. So if you're a network card and you're sending packets, and if it has to recover, it loses some state, which means that your end-to-end system kind of is out of whack. That's nothing they can do. So end-to-end, you have to figure out what this means, right? But for the most part, you assume that it works. You know what that means, right? What I'm saying, right? If you're writing to a disk or something, and if you had to reset, right? Some of the things that you might have caused some damage external to the system on the real world, right? Network packet might have been sent halfway through, a disk write may have started halfway through. Those would complete, but for the most case, you'll be fine if you can restore it, right? So the reality is, so the other thing to realize is UW works very closely with Microsoft, right? With the Microsoft research, and they're sort of next to each other, so they kind of know a lot of stuff. So they do interact with a lot of them. They know exactly what is going on within the Microsoft community more than what we can know. Many of them they cannot publish. I think one of you mentioned that it will be nice if they can do it for Microsoft. It will be nice, but practically Microsoft is not going to let one student come in and do the stuff, not because they don't want to, but because it's too much to ask one human being to look at the whole kernel and try to do this within Microsoft, right? So He didn't go to Microsoft, but if he had gone into Microsoft, he would have probably done this inside the company. But for now, Linux is the way for him to go. So it's a lot of lines of code, very popular, and there are lots of drivers here. So we have a lot of opportunity to do something. And similarly for Linux, there's a lot of lines of code, a lot of bugs, and to deal with, this is a real problem. So their goal is to have this notion of isolation, right? If anything happens, isolate it to the driver where it happened, be able to recover from it, right? And that depends on the way the driver was written, right? If a driver cannot recover because it's the way it's written, then you're out of luck. But most drivers are easy to recover, right? So the way they recover is you unload the driver, load a new driver, and try to bring it back to speed. And for the most part, it sort of works, right? And the key changes here is no code changes and no new languages. So no to spin, which is what they did a decade back. So no to the spin, no new operating system, no new perspective, no new hardware, except the tag thing is not a new hardware because it's out there. But what they're meaning is more like exokernel, right? Not a complete read. So it's not going to happen that Microsoft is going to dump the Intel everything and move to a completely new architecture which will solve all the problems. I mean, we are kind of stuck with the Intel stuff for a while, so let's stay within that, right? So they make some of the assumptions, which is very important to realize because that's what drives their work. So they assume that drivers are generally well behaved. If you don't assume that, you're in trouble anyway, right? Because you're loading drivers from other people. I think one of you mentioned that what happens if you have drivers sign certificates, right? That solves one little problem. It solves the problem of who wrote the driver, right? It doesn't solve the problem of whether it'll crash my machine. Because all it says is this driver came from HP. That's it, right? And basically it says Microsoft says that this driver was written by HP. So it's up to you to trust Microsoft, up to you to trust HP, but it doesn't say anything whether it'll crash your machine. So you don't need to be able to prevent all the crashes, right? This is to lower the expectations. So because people don't want to say you're not crashing all the crashes, so don't go for it. Be realistic. This is not trying to solve all the crashes. Especially if you have a bug which is not interacting with the rest of the system, they can't do anything. If you go into a loop, or if you deadlock or live lock or something inside your driver, this is not designed to do anything. So their principle is fault resistance. They assume faults will happen. You kind of monitor what is being asked, and then you resist them by capturing the state. And you design for mistakes, not abuse, right? So you're not looking for. So it's very easy to get away from this, but that's not the point, right? The driver can manipulate the page table, and all bets are off, right? And so why didn't they use microkernel-based approach? It doesn't do most of the stuff that they wanted, right? And I mean, it's a different philosophy, and you may be able to do some of the stuff with the microkernel, but not all the stuff that they wanted, right? So how would you do this in a microkernel-based system? Yeah.
And you could put the drivers in their own user-level server or in some sort of server, and then do
Yeah. Yeah, so you would have loaded the drivers into application level service, right? So you need to keep it outside the kernel, right? If it has to be part of the kernel, then there's nothing much microkernels won't buy you, right? If the microkernel needs to interact with it directly without the application process, then you are kind of stuck anyway, right? But for the cases where you can push it to application level service, recovery can be you basically start the application and you can proceed kind of thing, right? So some cases it will work, some other cases it may not work. So if it's part of the kernel mechanism, then you essentially do the same thing. You load the driver into the kernel, and that will fail too, right? So they had to tamp down the expectations because one of the things that this was a best paper award, right? So